you'll find it's not really linear in nature. You can see the numbers. This is looking off the A to D converter, which analog digital converter, which feeds my processor base. And I took a bunch of readings and I charted it all down. Now what this is going to work at, this is going to be the predicted values that it's supposed to be at. Now this is very critical because this is what you want the threshold to be at on these numbers. Now, let me show you this chart again. That one doesn't. Now, let me go back again. I'm going to go on to the next slide here. One second. Go on to the next one. Number 3. Number 4. This is another model sensor I came out with. This was a smaller, still holds all the same characteristics of the ones I just showed you. The one I first showed you happened to be used for pools for a chlorinization system. This one was used for it achieves all the same functions. It tells you the temperature rating, it tells you the salinity aspects of the water, and not only that, it tells you if there's flow or no flow of solution, because you need to know if your pump is on or off. When you don't want to keep your mechanism still running if the pump is still on. If the pump is off, so the feedback to say if there's no flow or no flow of solution.
Does this system generate enough heat that's needed in the car?
Okay. The heat comes from at 225 degrees open air. Let me talk a little bit about the principles of Brown's gas. Brown's gas implodes, but the implosion temperature is determined by the surrounding metals. For example, aluminum would have an apparatus temperature probably around 800 or 900 degrees. If you went to a steel block, it'd probably have 1100 degrees. It's the presence of that metals and axis of when the implosion, the spark occurs, determines the temperature which it happens at, which Brown's gas implode temperature at. If I took Brown's gas, poured it on the ground, and took a match and lit it, and it's floating around in the air, it'd be about 225 degrees. Could not run a car. But because of the metal surroundings from the cylinder itself, will cause an implosion temperature, which is comparable to gas. That would be regular gas that you have in your car today. Now, one of the things you got to be careful about if you have ceramics, let's say for some reason your rings had some ceramics in there, now your implosion temperature is going to be about 5,000 degrees. So as long as it's clean of these contaminants, that you must keep off your cylinder when you do this stuff, because that's one of the things you got to look at. But for the most cases, it should run fine. Let me go on to some other drawings. Show you here. Pull up number 5 here. Let's see here what we got here. This right here is showing you the digital readout that I put on my LCD. Just like I said, my sensor displays the temperature. Remember I was saying it tells you if there's no flow or flow of a solution? Well, you see the temperature change differential. There's actually 2 thermals inside that sensor. And what happens is it would see what the reference temperature is and see a difference of the heated. There's actually a heater unit. And there's no flow of solution, this number goes up and down. If there is flow of solution, of course it would go down. And I have these all charted out for the thresholds for water solutions. It works very well. This number here tells you the number of grams per liter of salt in solution. I also have it'll display the resistivity of water between the plates. Now the beauty of this of this sensor, it will go, like I said, 24 hours a day, 365 days a year, all the time. And the metal, and the actually I'm using the titanium plates on there, and they do not corrode because I'm using an isolated AC signal in there, so it does not electrolyze. A lot of the principles of the stuff that I'm going to be dealing with has to do with AC electrolysis, which keeps it clean. Now, these graphs that I was showing you before, which I'm going to show you again, because I'm always going to make reference to these graphs because, let me get them up here. Just bear with me a minute. That's a graph from the trigger. This one's just on the trigger points of when it's flow and no flow of solution. And I have it here, and this has all been put in my processor. If we go back on that board, there are actually 2 LEDs. Let me show you that. Show you that board again. Move it down. Let me see. It's over here. They're actually, this right here, there's 2 LEDs. It doesn't, and it would tell you if it's flow or no flow of solution. And if you take the water and you stir it, you see the LED goes to the other direction. If it's not no flow of solution, you can just, when you see it stop, you see the yellow LED go on. That's just so I'll be able to work with companies that, if they need a feedback to shut off their system, it lets them know if it needs to have a complete shut off, if there's something, if the motor's not working right or the water jets aren't working right. Let me go on to something else. Bear with me a minute. Bear with me. See if we get any more. See what we have over here. This comes up. Now allow me to open these. I'll show you more of my charts. Saw that.
Evan, while you're searching, can you answer a question?
Sure.
You're using AC electrolysis.
Correct.
Using a modified sine wave like Pure Rick used a very wacky sine wave when he did it. Or using straight standard AC sine wave, like coming out of a AC.
What I'm going to show you here,
Not to throw you off.
I have a board, electronic circuit board,